Have you ever wondered how these amazing robots or self-driving cars are able to discern a human being from an orange cone? How can we detect deer at night and in the morning from completely different views? We as humans excel at these tasks for safety and survival. So let's dive right in to see how we can give robots the same superpowers we possess by building artificial neurons. Let's start with a very simple example. Let's look at the image in the background here. And if I ask the question, does this image have a dog or a cat? As a human being, your answer would be very simple. It's like it has both. But if I ask you pick one, you only get a choice of is it a cat or is it a dog? You cannot say it's both. What would your answer be? Well, that depends, right? I mean, if the entire image is given to you and I am asking you, is this a cat or a dog? You might be able to see that, okay, the cat has more area occupied, or the more part of the cat is in the image. And so I would call this image a cat, right? Or maybe you like dogs more. And so you would say, okay, this image has a dog because I like dogs more. It totally depends upon the context of what you are looking for, right? So to make this problem a little more simpler for whatever we are trying to build, whatever model we are trying to build, let's crop it exactly at the object of interest. So in this particular case, it's the crop of a dog. So mostly the image has a dog. It has, of course, a table and something in the background, but let's ignore that for the moment. We are only asking the question, is this a cat or a dog, right? So on the left image, it's a dog. On the right image, it's a cat, right? The question is, if I ask you as a human being to describe to me, how did you get there? Like, how did you decide if the image on the left is a dog and the image on the right side is a cat? What would your answer be? The answer is fairly simple. You look for certain features which discern the dog as a dog and a cat as a cat. For example, you could be looking at the shape of the ears. The dog has floppy ears in this particular case and the cat has pointy ears. You might be looking at the nose. The dog has a big nose, which is big, and the cat has a smaller nose, which is as we see here, right? And or you might be able to look at the eyes. The shape of the pupil of the dog is round, but the shape of the pupil of the cat is basically like a vertical ellipse, right? So combination of all these things essentially tell us that this image either contains a dog or it contains a cat. And these are what we call as features in machine learning or computer vision. So we are going to denote this feature space as capital X, and it's going to have these three things. It could be a definition of the non-pointiness of the ears. It could be a round and large nose. It could be eyes without a pointy pupil, right? We can have the inverted version of the same as well, but this is just an example. A lot of the times, features might not be human readable like this, but in this particular case, for the example, it's easy to see something which is human understandable, right? And essentially what we have is this feature vector, which is going to have 3 numbers and color coded as red, green, and blue. So for the dog, it might be something like this. And for the cat, it might look something like this. If we essentially try to visualize how these feature vectors look, so what we have to do is we take the feature space X and we call each of the rows as X1, X2, and X3. And let's do a plot of X1, X2, and X3. So it's a 3-dimensional plot. We have 3 feature vectors here. So it's a 3-dimensional plot. And we are assuming that each of these are orthogonal to each other, which means that appearance of one feature does not impact the appearance of the other feature. So let's take each of these images and let's say we have a bunch of these images of dogs, a bunch of these images of cats. Let's take the feature vectors of each of these things. We will compute it. We will compress each image into essentially 3 values and we will plot it in this feature space. So let's do that. So if we plot the bunch of dogs, the dogs might be clumped up something like that. And if we plot the bunch of cats, it's going to look something like this. So if we were to write a mathematical function to say which is a dog and which is a cat, how would we do that? The answer is fairly simple. These two are beautifully separated by a linear plane, right? It's a 3-dimensional plane which cuts the space of dogs and cats into 2, right? And so this essentially is called linear regression, and we are going to find the equation of this plane which separates the dogs from cats. So let's do that. So let's define this function y, which is the output, which is a dog or a cat, as this function w transpose into x plus b, where x is the feature vector we have defined before, and w is the weight vector, and b is the bias vector. W and b essentially determine the orientation of this plane. So in other words, we can also write this by combining it into a linear matrix form. We are given pairs of labels and images, right? So we have an image which says it's a dog or a cat, and we have a bunch of these things. In other words, we have combinations of x and y. X is the feature vector from that image, and y is the label because we are given if it's a dog or a cat. We want to find basically w or b, and in the equation I have combined b into w, so it becomes another factor of w, and that's what that one is. So mathematically what we are trying to find is this. So we are trying to minimize the average values of the distance between my predicted, which is y tilde, and the ground truth, which is y hat, which is the ground truth label and the predicted label, and I'm essentially trying to find the weight vector, which includes the bias, which gives me this. This is essentially saying I'm trying to find the equation of the plane which gives me the most correct answer of dog versus cat. It's important to remember that here we are doing hard classification. It's either a cat or a dog, and there is no probability associated with it. You have to take a decision if it's a cat or a dog, right? Okay. So in other words, this y tilde is a function f, which is in this case a linear function of x and w, and bias is included in the x term. So we are fitting a linear hyperplane in n vector space, where n is 3 in this case because we have just 3 vectors. The question is, this is great, but we in real world want to get some probabilities, right? So having a hard classification is not that great. So what we want to do is we want to get the probabilities from the output function y. So how do we do that? You need some mathematical property function which essentially lets you do that. So to get the probability, we take this prediction y tilde and we apply some function g to get there. So what we will be at the end of the day be doing is that as you go away from the hyperplane, your probability of that particular class increases. So if you go on the left hand side, on the dog side, the probability of the dog given the image goes to 1, which means that probability of cat is going to 0. In the other extreme, you have the probability of cat given the image goes to 1, which means that the probability of dog goes to 0. And at any point in this space, we want the probability of the cat plus the probability of dog is equal to 1, because there are only 2 classes here. So what we want to do now is we want to have a function to get the probabilities, and this essentially becomes some squashing function. Remember that y could vary from -infinity to +infinity because it's a real number value. What we want to do is we want to compress that down to 0 to 1, which is the probability scale, 0 to 100%. Okay? So let's do that. So we have the probability of z, some value. Let's say in this case it could be y, given the dog. You could pick cat as well. It's the same exact thing will follow. And we have 0 in the middle, and we have the value of the function z or y on the x-axis, right? We want to go from y tilde to p, which means that we want to go from a real number mapping to 0 to 1 range. If you just do a simple linear mapping where you say like, hey, y tilde is equal to p or p is equal to y tilde, it's going to be a linear function. This is not that good because anything that is above the range of 0 to 1 is not helping us, right? A slightly better way to do this would be the sign function, where we say if it's negative, it belongs to one class. If it's positive, it belongs to the other class. And this is exactly what we did in the previous case of the linear regression, where we said, okay, it's on one side of the hyperplane, it becomes a dog. It's on the opposite side of the hyperplane, it becomes a cat. There was no real probabilities. It could flip from a cat to a dog just based on a little bit of noise. So even better way to do this is we smooth out this sign function using something called the logistic curve or the logistic equation, right? In this case, it's a smooth S-curve, and the smoothness of this S-curve basically determines how smooth my transition from cat to dog is or dog to cat is. This is great. Let's talk a little bit about logistic regression. Logistic regression essentially uses a sigmoid function to obtain the probabilities of classification. Mathematically, it is given as follows. It follows the sigmoid rule. And this is what gives us this beautiful smooth S-curve, right? Here, both the class probabilities are related using log odds, and this function z, which is w transpose x, is called logits. And this is super important because when you go and implement this in PyTorch or TensorFlow or any of these flavors, you will basically hear the word logits, which means for the raw output of that function without the probability. Sometimes logistic regression is also called a perceptron algorithm, as the olden day people called it. And perceptron is rarely the word used nowadays. It's logistic regression, but generally perceptron and logistic regression mean almost one and the same thing. Let's take another example. So if you have this image which went viral on the internet, this sort of has the features of both a cat and a dog. The question is, where would it end up in our feature space, right? It might end up something very close to the hyperplane, where if you do the probabilities like we did with the logistic regression, you might end up with something like 0.5, which means that I'm 50% likely that it's a dog, or in other words, it's 50% likely that it's a cat, and they're almost equal. So it's really hard for the classifier to say that I am not sure if it's a cat or a dog. And that makes sense. As a human, you would expect the same thing as well, which is rightfully so, because it's very confusing. The feature space is very confusing in this particular case. You might see that this might happen more often than not. As you include more pictures of dogs and more pictures of cats, you would see that some of these might be misclassified. The question is, how can we fix this, and why did this even happen? Right? Remember that we basically classified this space using a simple hyperplane or just a plane. In reality, this is never the case. It's indeed a manifold, which is a non-linear surface boundary. You can imagine it like a fabric in space, which is weaving, and that's separating the cats and the dogs, right? As there are more dogs that come closer to that, and the fabric weaves and warps, as there are more cats that go close to this green fabric, it will also bend and warp so that it accommodates these things as well, right? The classification boundary essentially is not linear. It's a non-linear function, map, or a manifold. And this is very true, and you see this a lot in the real world as well. If you recall, we had watched this in a previous video of color segmentation. The manifold is actually really complicated, right? It looked like a very fancy thing. Here we were trying to classify the color orange with respect to everything else. And it looked like a weird blobby function where we approximated with a bunch of Gaussian distribution values, right? So it's really hard. Gaussian mixture model is just one example of how you can do this, but there are better ways to do this for classification examples. Now let's take a little bit of bio-inspiration and let's see how nature actually does this. So in nature, these fundamental building blocks of nonlinear classifiers are built using a simple neuron. The neuron basically has a nucleus where the compute actually happens, and it has axons where the inputs and the outputs are coming from, right? So in this particular case, the axon is the one on the right hand side, the nucleus is the one on the left hand side. So the way these neurons communicate with each other to get input and throw out the output is through chemical exchanges. And people have studied this, and like the amount of chemical exchanged essentially responds to the amount or the value of the input or the output. So which is really, really cool. So let's build an artificial neuron. This is also called perceptron in the olden day literature. And this neuron is essentially a mathematical model of what actually happens in most of the animal brains, and including the brains of ours. So let's dive right in. This circle essentially represents the nucleus we just saw before. And we have a bunch of these like axons going in as the input, and let's call them x1, x2 up to xm. So we have m values of inputs going in, and each of them have some amount of chemical composition, which are basically these weight vectors, which is amplifying these values. So w1 to wm. And what happens is we want to basically combine them in this neuron. So you multiply x with the respective w, it's xi into wi, and you add them all up. And then what we want to do is there is a nonlinear computational block that's happening here, which essentially happens through this function sigma. So you apply this sigma on the sum of xi into wi, and then that becomes our output y. So if we want to write this out mathematically, y is given as this sigma function of w1 x1 plus w2 x2 up to wm xm. And we can obviously write this in a more concise form as w transpose x. Remember that the bias term we saw in the linear regression or the logistic regression still exists, that exactly exists in these inputs as well. So you can pretend that it's W transpose X plus B. And for simplicity, I'm not writing it, but in practice, when you implement it, you actually have that. So, and here capital W essentially is a stack of all these weight vectors, and capital X is a stack of all these like feature vectors x1 to xn. And this looks exactly like the logistic regression we talked about. This is beautiful. And this exactly was used for the classification of man versus woman in the 1950s and 1960s. And it was a really cool thing. So let's look at a video which basically talks about that.
In the 1950s and 60s, scientists built a few working perceptrons, as these artificial brains were called.
He's using it to explore the mysterious problem of how the brain learns.
This perceptron is being trained to recognize the difference between males and females. It is something that all of us can do easily, but few of us can explain how. To get a computer to do this would involve working out many complex rules about faces and writing a computer program. But this perceptron was simply given lots and lots of examples, including some with unusual hairstyles.
But when it comes to a beetle, the computer looks at facial features and hair outline and takes longer to learn what it's told by Dr. Taylor. Andrew Cruikshank's wig also causes a little heart-searching.
After training on lots of examples, it's given new faces it has never seen and is able to successfully distinguish male from female. It has learned. While promising, this approach to machine intelligence virtually died out.
So this is a really cool and interesting thing, but it's rarely enough to really do complicated tasks, because one neuron is too simple of a thing. It can be good enough for like classifying between man and woman or like cat and dog. But if you want to deploy this on a self-driving car, you might want to distinguish between 1,000 categories. And this does not really scale that well to the number of classes and the complexities in data. So what we will do in the next video is we will stack up a lot of these things together to build an even more powerful thing called a neural network. So stay tuned and subscribe to the channel for that video, because it's really exciting. So before we wrap up, let's just quickly recap. Why can't a linear classifier separate cats from dogs? Why does it not perfectly always work? Is a neuron a linear or a non-linear classifier? See you next time. Take care. Bye-bye.